January 1942, a frozen industrial yard on the outskirts of Chelyabinsk, Soviet Union. Steel plates lie stacked in the snow, their edges frosted white, their surfaces scarred from transport. Inside the factory hall, the air vibrates with the sound of generators and the sharp hiss of welding arcs. Orange light flares against concrete walls blackened by years of soot. Men in heavy coats stand watching a seam being drawn where doctrine says no seam should exist. The weld line cuts across the armor plate at an angle engineers have been taught to avoid. It looks wrong, untidy, almost careless. This weld is supposed to fail. At least, that is what the manuals insist. Under impact, stress should concentrate along the joint, cracking the hull like ice on a river. Shrapnel should burst inward, turning steel into a secondary weapon against the crew inside. That is what tradition predicts. That is why this method has already been dismissed as nonsense by supervisors and inspectors. Yet the engineer does not stop. He finishes the bead, steps back, and lets the metal cool. Outside these walls, German shells are tearing through tank hulls on the Eastern Front, killing crews even when armor is not fully penetrated. Something is wrong with how steel is being joined. And in this cold factory, one quiet experiment is about to challenge everything armies believe about armor strength, leading directly into the wider crisis facing armored warfare itself. By the time the Second World War erupted in September 1939, tank armor was already carrying decades of inherited assumptions. Designers across Europe believed protection was primarily a matter of thickness. Add more steel, increase the angle of the plate, and survivability would follow. What received far less attention was how those plates were joined together. Rivets, bolts, and weld seams were treated as secondary details, necessary compromises rather than critical components of protection. In peacetime testing, they rarely failed catastrophically. In war, they failed constantly. During the German invasion of Poland in September 1939, Polish tank crews reported a disturbing pattern. Vehicles struck by shells that failed to penetrate outright still produced lethal effects inside the hull. Rivet heads sheared loose under impact, flying through crew compartments at rifle velocity. Weld seams cracked even when armor plates remained intact. The phenomenon was poorly understood but devastatingly consistent. Armor was stopping shells, yet crews were still dying. The problem followed the war west. In France in May 1940, French and British tanks often possessed armor thickness equal to or greater than their German counterparts. On paper, vehicles like the Char B1 and Matilda II should have dominated the battlefield. Instead, many were disabled or abandoned after non-penetrating hits shattered internal fittings, jammed turrets, or wounded crews through spalling and seam failure. German after-action reports noted this with interest. The steel had held. The joints had not. Across the Channel, British investigators began compiling damage assessments from the Battle of France. Photographs showed cracked welds radiating outward from impact points like fractured glass. Riveted hulls exhibited patterns of internal fragmentation even where armor remained unbroken. Metallurgists realized that energy from shell impact was traveling through the armor plate and concentrating at its weakest structural points. The seams were behaving like fault lines. Germany faced the same problem, though its early victories masked it. During the campaigns in Poland and France, German tanks benefited from operational coordination and air support more than superior armor design. But when German vehicles encountered heavier Allied tanks, and later Soviet armor, the limitations became impossible to ignore. Early Panzer III and IV models suffered hull cracking and internal spalling under hits that did not fully penetrate. German engineers began quietly experimenting with improved welding techniques, though production demands limited radical change. Nowhere was the issue more severe than in the Soviet Union. When Operation Barbarossa began in June 1941, the Red Army possessed thousands of tanks, many hastily produced and inconsistently assembled. Early war Soviet designs relied heavily on welding, but quality varied dramatically between factories. Poorly trained welders, rushed schedules, and inadequate inspection meant seams often became structural liabilities. As German anti-tank guns found their range, Soviet tank losses mounted at catastrophic rates. Reports from the front painted a grim picture. Crews survived penetrations they should not have, and died in vehicles that appeared externally intact. Weld seams split under repeated shock. Armor plates shifted minutely, compromising structural integrity. Even when tanks were recovered, the damage was often irreparable. The issue was not only steel quality. It was how the steel was joined. Industrial realities compounded the problem. Wartime production demanded speed, standardization, and minimal waste. Factories were relocated, retooled, and staffed with workers who had little formal training. Welding manuals emphasized straight seams, uniform beads, and predictable angles. Deviations were discouraged because they complicated inspection and slowed assembly lines. Innovation was dangerous in an environment where consistency was valued above all else. By late 1941, the Red Army faced a brutal contradiction. It needed tanks faster than ever, but each loss carried an irreplaceable human cost. Investigators began to notice patterns emerging from wrecked hulls. Certain vehicles, often from specific factories or batches, showed fewer seam failures. Their welds looked different. Not cleaner. Not neater. Just different in geometry and placement. At first, these differences were dismissed as manufacturing irregularities. But as the data accumulated, coincidence became harder to argue. The war had reached a point where armor thickness alone was no longer enough. The battlefield was revealing truths that textbooks had overlooked. Steel was not just a barrier. It was a system. And somewhere within that system, a fundamental assumption was about to be challenged, leading directly to a deeper examination of how tanks were being built and who was willing to question the rules. By the winter of 1941, the Soviet Union's industrial evacuation east of the Urals was largely complete. Entire factories had been dismantled, loaded onto trains, and rebuilt in places like Chelyabinsk, Nizhny Tagil, and Sverdlovsk. Production halls were unfinished, roofs leaked snow, and machinery was often running before walls were fully erected. In these conditions, tank manufacturing became an exercise in controlled chaos. Speed was survival. Perfection was impossible. Standard welding doctrine at the time was rooted in pre-war engineering logic. Weld seams were expected to be short, straight, and placed where stress would be minimal. Corners were reinforced with overlapping plates. Joints were positioned away from expected impact zones. Inspectors looked for uniform beads and rejected anything that appeared irregular or unconventional. Strength was assumed to come from visual neatness and adherence to specification. What those specifications failed to account for was the physics of high-velocity impact. When an armor-piercing shell struck a tank hull, even without penetration, it released enormous kinetic energy into the steel. That energy traveled through the plate as shock waves, seeking the path of least resistance. In rigid, uniform structures, those waves converged at joints. The cleaner and straighter the seam, the more efficiently it acted as a stress concentrator. Soviet metallurgists had begun to observe this behavior during ballistic testing, but wartime urgency limited theoretical exploration. Tests were designed to determine whether armor stopped a shell, not how energy moved after impact. As long as penetration did not occur, results were often recorded as a success, even when weld cracking was evident. Crews, however, experienced a very different reality inside the hull. It was in this gap between test results and battlefield outcomes that one engineer began to question accepted practice. Working within the Soviet tank production system, he was not a celebrated designer or a political figure. He was a welding specialist, trained in metallurgy rather than tactics. His focus was not on thicker armor or new alloys, but on geometry, on how forces moved through metal. His observations were simple and deeply inconvenient. Straight welds, he argued, behaved like fault lines under shock. They allowed stress to propagate cleanly, amplifying damage at predictable points. What was needed was not smoother seams, but seams that disrupted energy flow. Irregular weld paths, angled joins, and interlocking geometries could force shock waves to disperse rather than concentrate. In theory, this would reduce cracking and internal spalling, even if armor thickness remained unchanged. To traditionalists, the idea sounded reckless. Irregular welds were harder to inspect, more difficult to standardize, and appeared weaker to the eye. Supervisors worried that deviating from established practice would slow production and increase failure rates. Some dismissed the concept outright, labeling it impractical and unscientific. In an environment where failure could carry political consequences, unconventional thinking was dangerous. Yet the engineer persisted. Using scrap plates and off-hours testing, he demonstrated that angled and staggered welds survived repeated impacts better than straight seams. Cracks that formed did not propagate as far. Plates absorbed shock more evenly. In some tests, hull sections with these unconventional welds withstood impacts that caused standard seams to fail catastrophically. The results were consistent, but they challenged deeply ingrained assumptions. Convincing authorities required more than theory. It required battlefield relevance. As frontline units continued to report inexplicable survivability differences between otherwise identical tanks, investigators began tracing those differences back to manufacturing details. Certain hulls, often produced under less strict oversight or by more experienced welders, exhibited precisely the irregular seam patterns the engineer advocated. They were not officially approved. They were improvisations. And they worked. Gradually, resistance softened. Not because doctrine had changed, but because necessity demanded it. Tank losses were unsustainable. Crews were irreplaceable. If a change in welding technique could improve survivability without slowing production or consuming more steel, it became difficult to argue against. What had been dismissed as nonsense was now being quietly reconsidered. The war was forcing a reckoning between appearance and performance, between tradition and physics. And as factories began experimenting under the pressure of combat demand, the stage was set for a broader examination of this single weld from multiple perspectives, each revealing a different facet of its significance. From the human perspective, the weld was never an abstract concept. It was a matter of survival measured in seconds and fragments of steel. Inside a tank, space was tight and unforgiving. Crews sat inches from the hull, surrounded by ammunition, fuel, and machinery. When a shell struck the exterior, even without penetrating, the impact could turn the interior into a killing chamber. Weld seams that cracked sent razor-edged spall tearing through flesh. A stronger joint meant fewer fragments, fewer wounds, and a chance to keep fighting. For crews who noticed that some tanks seemed to endure punishment better than others, the difference felt almost personal, though they could not see the welds that protected them. Tactically, the implications were immediate. A tank that survived a non-penetrating hit could remain in formation, maintain momentum, and protect infantry advancing behind it. Early in the war, many armored assaults stalled not because tanks were destroyed, but because they were disabled by internal damage. Jammed turrets, broken mounts, and wounded crews forced withdrawals. Improved weld integrity meant that a hit which once sidelined a vehicle became merely a shock. Units equipped with more resilient hulls could absorb fire and continue advancing, subtly shifting the balance in close engagements. Technologically, the weld represented a shift in how engineers understood armor behavior. Steel was no longer viewed as a static barrier but as a dynamic medium through which energy flowed. By breaking up straight seams and introducing angled or interlocking weld paths, the hull disrupted shockwave propagation. Energy dispersed across a wider area, reducing localized stress. This did not make the armor invulnerable. It made it more forgiving. In battlefield terms, forgiveness translated into survivability. From the enemy's angle, these changes altered expectations. German anti-tank gunners were trained to exploit known weaknesses. They aimed for joints, seams, and flat surfaces where armor was most likely to fail. As Soviet tanks began appearing that resisted cracking and spalling even when struck in these areas, gunners reported inconsistent results. Hits that should have disabled a vehicle no longer guaranteed success. The armor behaved unpredictably, forcing adjustments in aiming and engagement ranges. This unpredictability mattered. Anti-tank warfare relied on confidence and repetition. When outcomes became uncertain, hesitation followed. Crews fired extra rounds, exposed themselves longer, and risked counterfire. Small engineering changes inside a factory translated into subtle psychological pressure on the battlefield. At the same time, The unconventional Weld challenged leadership assumptions. Senior officers and factory managers had been trained to value uniformity. Anything irregular was suspect. Yet the data accumulating from the front was difficult to dismiss. Tanks with these unconventional seams were surviving more hits, returning from engagements that destroyed others. Reports did not speak of miraculous invulnerability, but of reduced damage, fewer casualties, and vehicles that could be repaired rather than scrapped. What made the situation uncomfortable was that the improvement did not come from a famous designer or a new model. It came from a detail most had ignored: a line of molten metal, drawn differently. And as these angles converged, human, tactical, technological, and enemy, the pressure grew to look at the Weld not as a minor manufacturing choice, but as a decisive factor shaping outcomes, leading directly into the broader implications that would soon follow. From the perspective of leadership, the Weld posed an uncomfortable dilemma. Wartime command structures were built to enforce consistency and minimize risk. Changes to production processes required approvals, retraining, and revised inspection standards. Every deviation threatened delays, and delays cost lives at the front. Yet ignoring evidence also carried a cost. Reports arriving from armored units were increasingly specific. Certain hulls resisted cracking. Certain factories produced tanks that returned more often. The correlation was becoming impossible to dismiss, even if the cause challenged established authority. For procurement officials and factory directors, the question was not whether the Weld worked in theory, but whether it could be trusted at scale. The unconventional seam required welders to think differently, to vary angles and paths instead of following straight lines dictated by templates. This introduced human judgment into a system designed to eliminate it. Critics argued that results depended too much on individual skill. Supporters countered that experienced welders already compensated intuitively, and formalizing the technique would actually improve consistency rather than undermine it. On the tactical level, field commanders began to notice changes that were difficult to quantify but easy to feel. Tanks that could absorb punishment altered how units maneuvered. Crews were more willing to push forward under fire, knowing that a single glancing hit was less likely to cripple them. Infantry trusted armored support that stayed in the fight longer. These shifts did not appear in official doctrine immediately, but they influenced decisions on the ground, shaping engagements in ways no blueprint could predict. There was also a moral dimension to the innovation. The engineer behind the Weld did not seek recognition. His work did not produce a new tank model or a dramatic battlefield debut. Instead, it quietly reduced casualties. In wartime narratives, such contributions often went unnoticed. There were no medals for improved seam geometry. Yet for the men inside the hulls, the difference was measured in whether a mission ended with a shaken crew or a silent compartment filled with steel fragments. Enemy analysts, too, were paying attention. German intelligence reports noted that later production Soviet tanks appeared more resistant to internal damage. Explanations varied, ranging from improved steel quality to exaggerated crew claims. Few suspected that the change lay not in the armor itself, but in the lines joining it. This misunderstanding delayed countermeasures and reinforced the advantage gained through a relatively simple manufacturing adjustment. The Weld also exposed a broader truth about warfare. Not all turning points are loud or immediate. Some unfold quietly, buried in production logs and repair statistics. By the time their impact becomes obvious, they are already embedded in the system. The unconventional Weld followed this pattern. It did not announce itself. It accumulated influence, hit by hit, crew by crew. As acceptance spread, what began as an isolated experiment started to reshape standard practice. Factories adjusted guidelines. Inspectors learned new criteria. Welders passed techniques from hand to hand. The process was gradual, uneven, and rarely acknowledged publicly. Yet by the time the war reached its most intense phases, the cumulative effect of these changes would be tested under the harshest possible conditions, where theory and hesitation gave way to decisive moments that could no longer be ignored. The true test came not in laboratories or factory yards, but under sustained fire. By mid-1943, the Eastern Front had become a grinding contest of armor against armor, where survivability was measured not by single engagements, but by endurance across weeks of combat. The Battle of Kursk loomed as the largest armored confrontation in history, and both sides understood that tanks would be struck repeatedly, sometimes dozens of times in a single day. In this environment, the difference between penetration and structural failure became critical. Soviet tank brigades entering the Kursk salient included vehicles produced across different factories and production runs. On paper, many were identical. Same armor thickness, same turret design, same engine. Yet after the first days of fighting, repair units began to notice a pattern that echoed earlier reports but now appeared on a massive scale. Some hulls absorbed multiple non-penetrating hits and returned to the line after minor repairs. Others split along seams after similar impacts and were written off entirely. Technical inspection teams documented the damage with increasing urgency. Hulls featuring irregular, angled, and staggered weld seams showed fewer long fracture lines. Where cracks appeared, they often stopped short, arrested by changes in seam direction. Spalling inside the fighting compartment was reduced. Mounts remained aligned. Turrets continued to traverse. These tanks were not untouched. They were battered, but they remained functional. In contrast, vehicles with traditional straight welds revealed familiar failure modes. Stress propagated cleanly along seam lines. Cracks lengthened with each impact. Even without penetration, repeated shock weakened the structure until catastrophic failure occurred. The difference was not dramatic in a single hit. It emerged over time, under cumulative punishment. Kursk provided that punishment in abundance. Commanders on the ground did not need metallurgical explanations to recognize value. They saw tanks that stayed in the fight, crews that survived engagements they would have previously lost, units that maintained cohesion under fire. Reports sent upward began to reflect this reality, not in technical language, but in outcomes. Fewer abandoned vehicles, more recoverable hulls, improved crew survival rates. German anti-tank units, meanwhile, encountered unexpected resistance. Guns calibrated to exploit known weak points produced inconsistent results. Hits that should have disabled tanks forced crews to expend additional ammunition or reposition under return fire. In some sectors, this delay proved costly. Soviet armor, even when outgunned, absorbed enough punishment to disrupt German attack schedules and blunt momentum. The data accumulating from Kursk and subsequent operations carried weight no theoretical argument could match. This was not a controlled experiment. It was war at its most unforgiving. The weld was being tested under repeated impacts, variable angles, and extreme stress. And it was holding. Behind the lines, factory engineers and military inspectors reviewed after-action reports with a new urgency. What had once been tolerated as an irregularity now appeared as a survival advantage. The question was no longer whether the unconventional weld worked, but whether the army could afford not to adopt it universally. The answer was forming in steel and blood, setting the stage for decisions that would formalize what the battlefield had already confirmed. By late 1943, the evidence had become institutional rather than anecdotal. Central repair depots compiled statistics comparing hull damage across production batches. The patterns were consistent enough to survive bureaucratic scrutiny. Tanks with disrupted seam geometry showed markedly fewer structural failures after non-penetrating hits. They required fewer man-hours to repair and return to service more quickly. In a war of attrition, this mattered as much as outright destruction. Formal testing followed. Armor sections were welded using both traditional straight seams and the unconventional angled and interlocking methods. These sections were subjected to repeated ballistic impacts under controlled conditions. The results mirrored what frontline mechanics had already observed. Straight seams concentrated stress and encouraged crack propagation. Irregular seams dispersed energy, reducing fracture length and internal spalling. In some tests, hull sections using the new technique withstood impacts that caused traditional seams to fail after fewer strikes. The findings forced a shift in doctrine. Welding manuals were revised, not publicly or ceremonially, but through incremental changes in guidelines and inspection criteria. Welders were instructed to vary seam paths, avoid long, uninterrupted lines, and prioritize energy disruption over visual uniformity. Training programs adapted. Inspectors learned to look past superficial neatness and evaluate structural intent. What once would have been rejected as sloppy was now recognized as functional. The engineer whose ideas had sparked this change did not stand before a committee to accept accolades. His contribution was absorbed into the system, anonymized by necessity and wartime secrecy. The priority was not credit, but continuity. Tanks were needed at the front, and the front was consuming them faster than ever. Any improvement that extended a hull's life by even a few engagements was invaluable. As production standardized the new welding approach, its effects became more pronounced. Late-war Soviet tanks exhibited a resilience that earlier models lacked, even when facing more powerful German anti-tank weapons. Armor thickness had increased, but so had structural integrity. Hulls behaved as cohesive units rather than collections of plates joined by vulnerable lines. German engineers, encountering these vehicles, struggled to isolate the cause. Assumptions focused on steel quality or casting improvements. The idea that weld geometry could double effective strength without adding material was counterintuitive to prevailing thought. By the time similar concepts began to appear in German and Allied production, the war's trajectory was already shifting. The turning point was not marked by a single order or announcement. It was marked by absence. Fewer reports of seam failure. Fewer crews killed by internal spall. Fewer tanks lost to damage that once would have been inevitable. The Weld did not win battles on its own, but it removed a silent weakness, allowing armored forces to function closer to their theoretical potential. As the war pushed westward and production continued under relentless pressure, the consequences of this quiet decision unfolded across thousands of hulls and tens of thousands of lives, shaping the aftermath in ways that extended far beyond the factories where the idea had first been dismissed. The immediate aftermath of adopting the new welding approach was not dramatic, but it was measurable. Repair depots across the Eastern Front reported a steady decline in hulls written off due to structural failure alone. Tanks that would previously have been abandoned after suffering cracked seams were now being recovered, repaired, and returned to service. This reduced the strain on production lines and eased the relentless demand for replacements. In a war defined by material exhaustion, such efficiencies carried strategic weight. Crew survival statistics reflected the change even more clearly. While exact figures varied by unit and engagement, internal reports noted fewer casualties from non-penetrating hits. Spalling injuries declined. Instances of weld seam rupture leading to catastrophic internal damage became less frequent. Crews who survived multiple engagements developed a cautious confidence in their vehicles, an intangible but important factor in combat effectiveness. Morale improved not because tanks were invulnerable, but because they were more predictable under fire. Factories, once resistant to deviation, adjusted their workflows. Welding stations were reorganized to accommodate angled and staggered seams. Quality control standards evolved, emphasizing structural resilience over cosmetic uniformity. Experienced welders became valued not just for speed, but for judgment. Their ability to adapt seam geometry to hull shape and thickness was recognized as a skill rather than a liability. This shift subtly altered labor dynamics within tank plants, elevating practical expertise. The engineer at the center of the innovation remained largely invisible in official narratives. Wartime secrecy and collective attribution ensured that no single name dominated the story. In some internal documents, the technique was referenced simply as an improved seam method or a reinforced weld pattern. Credit, where it existed, was distributed across departments rather than individuals. This anonymity was typical of wartime engineering, where results mattered more than recognition. As the Red Army advanced westward in 1944 and 1945, tanks produced with the improved welding technique faced increasingly powerful German weapons. High-velocity guns, shaped charges, and heavier anti-tank defenses tested every aspect of armor design. The weld did not make tanks immune. Penetrations still occurred. Vehicles were still lost. But the margin between survival and destruction narrowed in favor of the crew. In post-engagement inspections, analysts noted that even when penetrated, Hulls with disrupted seam geometry were less likely to fail catastrophically. Damage was more localized. Structural collapse was rarer. These observations reinforced the value of the approach and justified its continued use even as designs evolved and armor thickness increased. By the time the war in Europe ended, the unconventional weld had become standard practice, no longer controversial or noteworthy. It was simply how tanks were built. Its quiet success set the stage for a broader reassessment of armored vehicle construction in the post-war world, where lessons learned under fire would influence doctrine and design far beyond the conflict itself. In the years following the war, the lessons learned in haste were examined in calm. Engineers and military analysts revisited wartime production records, damage reports, and ballistic test data with a clarity that combat had not allowed. The role of weld geometry in armor survivability emerged as a documented principle rather than an improvised solution. What had once been tolerated as an irregularity was now formalized as best practice. Post-war tank development programs in the Soviet Union incorporated these insights from the outset. New hull designs treated weld seams as structural elements rather than necessary compromises. Angled joins, staggered seams, and deliberate disruption of stress paths became standard considerations in layout planning. Welding manuals were rewritten to reflect an understanding of energy distribution under impact, embedding wartime experience into peacetime doctrine. The influence extended beyond one nation. Allied engineers, analyzing captured vehicles and shared reports, reached similar conclusions. In both NATO and Warsaw Pact designs, emphasis shifted toward hull integrity as a system. Casting, welding, and later composite construction all reflected an awareness that how materials were joined could be as important as the materials themselves. The idea that effective armor could be strengthened without adding weight aligned perfectly with the emerging demands of mobility and firepower in the Cold War era. Technological progress amplified the lesson. As anti-tank weapons grew more powerful, survivability depended increasingly on managing damage rather than preventing it entirely. The principle pioneered by that unconventional weld, dispersing energy, preventing catastrophic failure, and preserving crew space, found expression in spall liners, layered armor, and modular construction. Each owed something to the wartime realization that resilience was not binary, but cumulative. The engineer's contribution remained largely anonymous in official histories, but its legacy endured in steel. Every hull that survived long enough to be repaired, every crew that escaped injury from a glancing hit, traced its lineage back to a moment when accepted wisdom was questioned under pressure. The weld had not been a miracle. It was an application of physics, observed, tested, and proven in the most unforgiving laboratory imaginable. In modern armored warfare, the principle remains intact. Designers continue to focus on how structures fail, not just how they resist. Damage control, crew survivability, and system redundancy all reflect a mindset shaped by wartime experience. The unconventional weld, once dismissed as nonsense, became part of the foundation upon which contemporary armored design rests. As time passed and the conflict receded into history, the story of that weld faded into technical archives and manufacturing standards. Yet its significance endured, quietly linking the urgency of wartime improvisation to the deliberate evolution of military technology, inviting reflection on how small decisions can shape outcomes far beyond their moment. War is often remembered through the names of battles and commanders, through sweeping offensives and dramatic turning points. Yet much of its outcome is decided far from the front lines, in places where no shots are fired and no flags are raised. The story of this weld belongs to that quieter world. It is a reminder that survival in modern warfare depends not only on courage or strategy, but on understanding how materials behave when pushed to their limits. The engineer who challenged conventional welding doctrine did not change the course of the war alone. He did not design a revolutionary tank or command an army. He observed a pattern others overlooked and trusted physics over appearance. In doing so, he revealed a truth that combat would confirm repeatedly: strength is not always a matter of mass, but of structure. Steel does not fail because it is thin, but because force is allowed to gather where it should not. Inside armored hulls, That insight translated into lives spared from invisible dangers. A weld that disrupted shock saved crews from fragments they never saw coming. It gave machines the resilience to endure one more hit, one more mission, one more chance to return home. These gains were modest individually, but immense in aggregate, multiplied across thousands of vehicles and years of fighting. History often celebrates innovation when it is loud and unmistakable. This innovation was neither. It arrived quietly, resisted quietly, and proved itself quietly under fire. By the time it was accepted, it no longer seemed revolutionary. It simply worked. And perhaps that is the highest measure of success in wartime engineering. Long after the factories fell silent and the battlefields grew still, the principle endured. In every armored vehicle built since, the question remains not just how thick the armor is, but how it holds together when struck. The answer traces back to a line of molten steel drawn against convention, at a moment when questioning the rules mattered more than following them.